Hey, what's up, everyone? We are in Chapter 3, so let's go ahead and get started. Exponential functions. Okay, we'll call this section 3.1. Now, a few things. I'm just going to do some notes here, and then they'll kind of cover the entire section, and then we'll do a couple different homework sections. And so we'll spend a couple days on this section. So exponential functions, section 3.1. So what does one of these look like? Well, it looks like this. F of x equals a times b to the x power. So a and b are both some numbers. So an exponential function could be this. It could be, I don't know, 3 times 2 to the x power. I'll just put a y there for now. This is a particular exponential function. Okay, let's look at what's going to happen here. Let's make a little chart here of x's and y's. We'll go to 0, 1, 2, 3. Okay, let's plug these numbers in. 2 to the 0 power, well, anything to the 0 power is 1. 1 times 3 would just be 3. 2 to the first power is 2 times 3 is 6. 2 to the second power is 4 times 3 is 12. And 2 to the third power is 8 times 3 is 24. Okay, so this is, you can see these numbers are getting bigger. In fact, they double each time, right? We're multiplying by 2. And that is, that's no coincidence. This base of 2 is always going to do that. Whatever the base is, that's going to multiply each time as it's going up. And you also have the 3 there. Let me get a different color here. You also have the 3 here, and that is going to be your initial value. Okay, the 3 is going to be where it starts, at 0. Because anything to the 0 power, that'll go away, leaving you with whatever's out front. So sometimes we will call A the initial value. Sometimes we will call B the multiplier. Well, what could these numbers be? Well, A, the value of A can't be 0, right? Because 0 times anything would just make the whole thing 0, and that would be incredibly boring. That would make this a constant function. So let's go ahead and note that A can't be 0. And for B, for us to stay within the realm of real numbers, B can't be negative, can't be 0 either, or it would just cancel out everything. So I'm going to make a note about a couple different things where B could be. Okay, if B is greater than 1, we have growth. If B, well, I want to say this a little differently. If 0 is less than B, is less than 1. So if B is between 0 and 1, we have what we call decay. Exponential decay. Okay, we could have this in other forms as well. So let's see. You could also sometimes see y equals e to the x power. E is a very special number. It has to do with finance, but it also has some interesting properties in calculus. I would encourage you to go to Wolfram Alpha and watch a couple videos on that because they're pretty good. He would explain it better than me anyway. And another way to write this equation is y equals a, then e to the k x power. And if you do a little bit of math, I could rewrite this function, 3 times 2 to the x power, into this form right here. The initial value would still be 3, and you can choose a value of k that will give you the same results as choosing this base of 2 here. So this is another way to write this first equation, and this is one of our 12 basic functions, the exponential function. Yes, and let's go ahead and I have one other little note here for that. E is about 2.7818. This is a very special irrational number. This is on the level of pi. This is one of our fundamental numbers in mathematics. The other kind of function I want to talk about here is the logistic. The logistic function, and the basic form looks like this. Let's say g of x, I'll use a new letter here, is equal to 1 over 1 plus e to the negative x. And a logistic function is interesting because it has two different horizontal asymptotes. This is why we sometimes use it for modeling populations, because population in an area can grow, but at a certain point it has to stop, capped off, and people have to move elsewhere. So a logistic function, whoops, that's terrible. Oh well, I'll go with it, has two horizontal asymptotes. And you can adjust this however you want. And it starts at one and it goes to the other. So that's a logistic function. It has a base, and then it will go up to some other horizontal asymptote. And again, this can be useful with populations, because in a certain area it can only support so many people, so then it would be capped off. So that's your general logistic function.